me review what we did last time, right? The low noise amplifier. The main thing we care about is that the noise factor and noise figure. So first of all, we introduced the concept of signal to noise ratio, SNR. This probably is easy to understand. We care about the signal that we want, how much more it is over the noise. So the SNR is just the signal power divided by the noise power. Again, power is what? Power, of course, is V squared divided by R, or I squared times R, right? But again, we don't care about R because in all our RF design, we have on the chip, we have a characteristic impedance, for example, 50 ohm, 100 ohm, right? So we can take the R away, just like when we're handling the noise, we also just take away the R, the ohm, right? So it's just like V square of the signal divided V square of the noise, right? This should be very straightforward. You should be able to memorize it, right? Any questions about signal to noise ratio? Now, if no, then the issue is this. This is the input. I have this amount of signal and I have this amount of noise. After an amplifier, the signal got amplified. The noise also got amplified. They will be amplified by the same amount, right? Like 10 dB, right? Or increased by 10 dB. But the amplifier itself is formed by resistor and transistors, and we have learned the noise that can be generated by the resistor and transistors, right? Like the white noise, the gate resistant noise, which is also the white noise, the flicker noise. Remember all this? So the amplifier itself is going to add additional noise to it. So the total noise is not just what the amplification of the noise in the input, but it's amplification plus the noise added by the amplifier, right? So in the input, I have a certain signal to noise ratio, right? This can come from another circuit, like the transmitter, right? But after, like you talk to the mic, but when the mic amplify your sound, it also amplifies the noise. At the same time, it increases the noise by this amount, C dash. So now the signal to noise ratio is this A dash divided by B dash plus C dash. And A dash, of course, is the gain times the input A, right? It's just gain A, gain times A. And of course, this B dash is just the gain times B. But you have additional C dash. If you don't add any C dash, the gain will get cancelled out. You have the same signal to noise ratio. But because you add additional noise from the amplifier or any circuit that you are using, your signal to noise ratio is going to reduce, getting worse. Is this okay? Right, so we usually have smaller signal to noise ratio at the output than in the input. Then how do we characterize this? We use something called noise factor. It is easy to understand. The input signal to noise ratio divided by the output signal to noise ratio, right? Because the signal to noise ratio degrade, right? So your noise factor is going to be larger or equal to 1. At the best case, it's equal to 1, but it's impossible. You always will add additional noise to it. Okay, so this one sometimes is confusing. I remember a student interviewed a big company and they asked him what's the signal to the noise factor, and he said it's signal to noise ratio input divided by the output. So somehow the interviewer, the engineer, keeps saying that he's wrong. So you see, it's very confusing. Of course, that engineer was wrong, right? It should be input divided by the output. Okay, so do not mess up. Now, then we have another factor called noise figure. Another matrix called noise figure. It is very convenient because in the amplification, we usually use dB, right? So it is easy. It is just you take the log of the noise factor times 10 and express in the units of dB. And what is dB? Now, dB is actually like this. Maybe last time I did not really say it clear enough. Usually, it is a signal. And you reference to the reference signal. Okay, and you take the log. If it's just voltage, we'll take 20, because this is equals to 10 log V squared divided by V ref squared. So dB is more talk about reference to a particular power, how much power you have. So if you reference to it and then take the log times 10, that is the dB. Now, what is the reference power? We actually reference it to 1 volt. Okay, so when I say how much dB the signal is, it's just a refer to 1 volt. You may hear about dBm, then it refers to 1 millivolt. Okay, so if I have a 1 volt of power, 1 divided by 1 is 0, then it's how many dB? 1 divided by 1 is 1. So what is that? How much dB is that? 0 dB, right? 0 dB means you have the same level as the reference. Give you another question. So 1 dB, 0 dB equals how much dBm? If you reference to 1 millivolt. Reference to 1 volt is 0, right? Because take the log of 1 divided by 1. But how about in dBm? So dB is talking about log uh, 10 times log 1 volt divided by 1 volt, right? That is 0 dB. This one is talking about 10 log 1 volt divided by 1 millivolt. What is that? What is 1 volt divided by 1 millivolt? Hmm? 1,000. They are both watts, right? So it's 1,000. What is log 1,000? 3. So how many dBm? How much dBm? 30 dBm. Okay. Now this is referred to the value, but we also will talk about the gain in dB, right? So dB doesn't. You need to look at the context. Sometimes it's just saying that I try to find out the 10 log that value. For example, in the noise figure, we're just comparing the signal to noise ratio of the input and output. So then here I may get, let's say, 3 dB, for example, 3 dB signal to noise figure. Sometimes we're talking about how much energy it has, how much power it has. Then it has this meaning. Sometimes we talk about the gain. For example, it's 10 times, right? Then if it is 10 times, how much dB do we have? Just the equation, 10 log 10. What is that? 10 dB, right? Very good. So we'll keep looking into this, right? So I just remind you this if you forgot. Or any questions? But the main point on this slide is understand what is signal to noise ratio and what is noise factor and noise figure. And don't make mistake, right? And you should be able to appreciate and understand it. This is the basic. Okay, any questions? Okay, if no, then we go back to the noise factor calculation. Here I show you an L19A, just an amplifier. Now, but as we have been doing, what we do is that we convert it to a noisy-less circuit and say that effectively it gives me this much of noise power. Again, noise power is in Vn square bar, right? It's just like the root mean square. Not really root mean square because we integrate it, then we will get the, sorry, this is not like the variance. But this is not the real variance because we integrate it, we will get the FH, the root mean square of the real power. Right? We discussed this in a few slides before. But anyway, now at least you know it's Vn square bar. So this represents the real circuit. Is that okay? Yeah.
So Vn square.
Say again?
So V square
No, Vn square is the effective noise you see from the output. Do you see that we put it in the output? So it's just like I don't have noise for this circuit, but somehow at the output it present me that amount, this much of noise at the output. This is the output, right? Related to what? To Z? To which one? Okay, I see what you mean. Yes, very good. So he's saying that is this C prime equal to this Vn square? Yes, in this sense, yes. Because here I kind of say that I have an effective noise generator at the output. Although it's not actually at the output, it actually generates from inside, but through all the transformation, it presents as C dash, correct? So this is just like the C dash in the previous slide. Good point, yeah. Now, so if I have a signal coming in, right? So I have a voltage, any signal will have an output impedance, Rs. And this signal also has its own noise. But if you remember the theory we taught before, if you look into the two ports, the effective noise generated by this port is equal to 4kT, the real part of this port. Now, so here we assume there's no reactive element, there's no capacitor, no inductor. So there's no imaginary part, right? So this noise must be 4kT Rs. So anyway, if I have a voltage source with an effective output impedance of Rs, the noise that it will present to us is 4kT Rs, which is Vn square Rs here, right? But the value is 4kT Rs. Make sense? Anyone has question? Looks like a little bit confusing. Okay. Now, then what is the noise factor here? Now, we do need to be careful. Our goal is to find out what is the ratio of the signal to noise at the output and the signal to noise at the input, right? But first of all, I need to point out that how much noise really come into here. This one has an output impedance of Rs, and this one has an input impedance of Cn. So by the potential dividing effect, right, the voltage divider, the voltage seen by the input of this L19A is actually just Zin divided by Rs plus Zin times Vin, right? So I call this alpha. So you actually scale, because if I put, let's say, 1 nanovolt here, what I see here is alpha times 1 nanovolt. I mean, yeah, if 1 volt, that is 1 volt times alpha. But now I care about the noise, right? So the noise is going to be square root of Vn square Rs. So, but however, we don't care the absolute value, we care about the power. So what the noise that I see at L19A is going to be the noise from the Vn square Rs times alpha square, right? Because voltage is times alpha, then the power is times alpha square, right? So here tells us that this is the noise seen by L19A. But of course, it is also the voltage also scaled by that much, right? So in the input, the voltage seen by this L19A, which is the input power, signal power, is actually alpha Vin square. Do you agree with this? Alpha Vin square. If you have 1 volt, then you don't get 1 volt here. You get alpha times 1 volt. But the noise is also got scaled by alpha square. So they got cancelled. So it doesn't matter. That makes sense, right? Because the noise and the signal all see the potential divider circuit, right? Resistor divide, the ladder. So it is still Vin dash over Vin dash Rs square. So this is the signal to noise ratio at the input to the L19A. Make sense? Any questions? Yeah. Which one? V in square? Thank you. So very good point. So what he's trying to say is that I should not put, no. I can put V in, but because I still put V in dash here, so here is referring to the whole thing, alpha square times Vn square. Do you see what I mean? Here I did not cancel alpha square. I just represent the whole term as V in dash. Where V in dash equal to alpha times V in. And then here Vn dash square equal to alpha square times Vn square. Make sense? Because both of them have dash. But he is right, because actually this is confusing, right? He thought that I cancel it out, and actually I should. This is also equal to V in divided by Vn square Rs square. Right? That is what you are asking, right? Yeah. But when I do this, I also need to remove the dash in the denominator. Here I have both dash, here I don't have. Okay, this is the scale version ratio, this is before scale, and they should be the same because alpha square are the same. Although this is confusing, but try to look into this, because this will determine that you have a feeling about all these potential divider and what you're dealing with now. We're talking about signal to noise ratio. How about the output? Now, output, what is the signal? Of course, there is V in square alpha square times AV square. AV is the gain of the circuit. Okay? Then the noise is the noise, same. AV square, the whole thing get a gain. But then you add an additional Vn square. Okay? So you do signal to noise input out SNR divided by output SNR to get the noise factor. You just do the math, right? So how do we do it? This one, I just copy here. This is signal to noise ratio input. And divided by this one, then it's multiplied by the denominator, divided by the numerator. I just flip it, right? And then you see this one got cancelled. And then this one times this one is just this one. You give me 1. And then this one divided by this one. So what I have been doing, we'll go to the next slide to see more. But basically, from here, you see the noise figure is always equal to 1 plus something, plus what? Plus the noise that you generated by your amplifier normalized by the gain, the impedance, this matching. Alpha is due to this impedance matching. And then normalized by the input noise. So if you have different input noise, your noise factor actually will change. Here give a better picture, right? So what we are showing in the previous slide is actually equation 2. So we calculate the output noise due to the amplifier, Vn square. Here, Vn square. We divide it by the gain, the overall gain, so it also including alpha. And then we normalize it to the 4kTRS, the input noise. Okay, and plus 1. This is a way to memorize the noise factor. Right, so again, noise factor is due to the additional noise added by your amplifier. So definitely, you have this Vn square. This is the noise added by your amplifier. But you need to, it depends on the gain. So then you just divide by the gain. So you actually bring it to here. And then normalize by whatever you have in the input noise. Right? So this is a way to memorize it. You just bring it from the output to the input. So they are at the same footing. And then you normalize it. Okay? Another way is this, which is exactly the same as this one. This is just before, this is just that, this is the noise due the amplifier. Here, this is the total noise, right? Due to the source and the amplifier. So if you know what is the total noise at the output, again, all you need to do is just divide it by the gain and the impedance matching and normalize to it. And this is equivalent to this one. This equation is actually talking about this equation that I'm showing you. Okay? And this equation is about this one before the simplification. Any questions? Please take a look. Yeah.
When you're trying to design your amplifier and figure out, or I guess minimize your unit squared, kind of working with some sort of noise range, right? Because it looks like the noise factor depends on the.
I mean, noise of the input is something you probably cannot change because it is usually like a characteristic impedance that coming in, right?
Yeah, but it looks like you're optimizing for a certain.
You will optimize this one and this one together, right? So you want to make Vn small enough and V and A large enough. So that is a trade-off, right? You can have very high gain, but at the same time you can add a lot of noise from your amplifier. So this is what you want to optimize.
Yeah, but
Correct, but noise figure again is just a human defined factor, right? This input noise really depends on the characteristic impedance. You need to have an impedance in your circuit. It cannot be 0, and usually it's 50 ohm. And the point is that if you make this small, actually, it might be difficult because you need to optimize the whole system if you try to touch the RS. So you would just assume that you are given 50 ohm or 100 ohm, whatever.
also.
Yeah, if you decided to have that system 50 ohm, yeah. Because now it's only talking about the ratio. Although you say, yeah, I make this smaller, looks like I have a worse NF, but actually really doesn't matter because this is really talking about how much more I add to it. You're still adding so much noise to it, absolutely, right? It's just that this becomes less meaningless. So what you want to optimize is the noise generated by it and the gain. And that's why in quantum computing, your first stage is to have a low gain, but also low at the noise. So you don't want to create a very large amplification, but at the same time, you have a lot of noise. So that's why you use quantum limiter amplifier. The gain is not good enough, but you add the minimum amount of noise that you need to add. Then you have another stage to further do the amplification. And later you will see that the noise in the subsequent states becomes not that important because they're going to be attenuated by the gain in the previous state, the available power gain. Yeah, so that is the optimization that you are talking about. I want to find an amplifier that has low enough noise and with a reasonable gain. Yeah. So that is a good point. Now, let's take a look. We are going to there very soon. So let's practice the noise figure.